In this video, we will give an overview of improper integration. So let's start off with a motivating example. Let's evaluate and interpret the quantity a of t equals a definite integral from 0 to t of 1 over 1 plus x squared, where here the assumption is that t is bigger than 0. So let's first start off with the geometric interpretation. To how a definite integral is defined, and using the fact that the function 1 over 1 plus x squared is positive, a of t is going to represent the area enclosed between the curve, y equals 1 over 1 plus x squared, and the x-axis going from x equals 0 to x equals t. So from a graphical perspective, if we consider the graph of 1 over 1 plus x squared, a of t represents the area enclosed between 0 and x equals t. So a of t is the quantity represented by this area. So let's go ahead and calculate it. So a of t is the definite integral from 0 to 2 of 1 over 1 plus x squared. An antiderivative of 1 over 1 plus x squared is arctangent of x. And we need to evaluate this from 0 to t. So this is equal to arctangent of t minus arctangent of 0. But arctangent of 0 is 0, so I'll leave it simply as arctangent of t. And the big observation, and the reason this is a motivating example, is to make the observation that if we take the limit as t goes to infinity of a of t, what we get back is the limit as t approaches infinity of arctangent, which is the number pi over 2. And what this is actually representing is that if we go back to this more geometric interpretation for the function 1 over 1 plus x squared, if you look at the amount of area enclosed underneath this curve going from 0 to infinity, this enclosed area is pi over 2 units squared. And this really leads us into the idea of what we would call a type 1 improper integral. So an improper integral of type 1 is where we are integrating either from a number to infinity or minus infinity to a number. In either case, what we do is we break it down in terms of a more reasonable problem and use a limit. So if we have the integral from a to infinity of a function, we instead first calculate from a to some number t, and then evaluate the limit as t goes to infinity. And similarly, for an integral from minus infinity to b. This improper integral is called convergent if the limit on the right-hand side exists, and divergent if the limit does not. And then another very big observation is that if the improper integral from a to infinity and minus infinity to a of a function converge, and we need both of them to converge, then we can evaluate the integral from minus infinity to infinity by just adding up those two quantities. But once again, note we can only do this if both of these integrals simultaneously converge. So as mentioned a moment ago, we view this improper integral as a limit. And in terms of some special integrals that we can maybe expect to see in the future, integrals of the form from 1 to infinity of 1 over x to the p, where p is a real number, we might refer to as p integrals. And they are going to converge precisely when p is larger than 1 and diverge for p less than or equal to 1. If f of x is not continuous at one of these limits of integration, say at a, then we cannot apply the fundamental theorem of calculus to evaluate this, and we will call it an improper integral of type 2. And in this case, it also must be viewed as a limit, where we evaluate the definite integral from t to b, and we let t approach a. In this case, it would be from the right-hand side. So this should be a plus. And then something that can be useful is the comparison test that allows us to determine if an integral converges or diverges without actually having to evaluate, simply by comparing to an integral where we already know the behavior. Typically, something like maybe one of these p integrals. So the comparison test tells us that if you have this inequality satisfied, and if you know the improper integral of the larger function converges, well then, so does the smaller function, because you're enclosing less area. If the improper integral of the smaller function diverges, then so does the improper integral of the larger function. So let's finish with a simple example. So let's evaluate the improper integral from 1 to infinity of 1 over x squared. Now, the first step for evaluating an improper integral is to rewrite it as a limit. So we will write this as a limit as t approaches infinity of the definite integral from 1 to t of 1 over x squared dx. We now evaluate this resulting integral using the fundamental theorem of calculus, and then we take the limit. So an antiderivative of 1 over x squared is the quantity minus 1 over x, and we're evaluating from 1 to t. So this would be the limit as t goes to infinity of minus 1 over t minus a minus 1. So I'm going to write that quantity as 1 minus 1 over t. As t goes to infinity, the limit of a constant is that constant, and 1 over t is approaching 0. So in this case, we would say that the improper integral converges, and the value that it converges to is 1.